Hi, so this video is going to be going over the CFG to PDA conversion for a particular context-free grammar, and in this case, it's the set of all strings that are not palindromes. So let's review the grammar to make sure it actually isn't palindromes, but it doesn't actually matter. So we have the start variable here, although I have not indicated that, which I should do. So I will indicate that this is the start variable. But of course, P could be the variable that's the start variable, but it doesn't really, but it wouldn't actually make a, of course, P could be the start variable. Of course, P could be the start variable, but it doesn't reach S, so it doesn't really make sense. But it's important to mark the start variable. So if we have a string that is not a palindrome, then that means that before, so if we have a string that is not a palindrome, then that means if we have a string that's not a palindrome, then the same distance from either end of the string must have different characters. So let's think about that. Well, in order for this grammar to make a string, we need to hit this particular empty string down here because every other rule has some variable in it. And so we need to get down here from S, which means we must hit one of these two rules because these two involve S and that's not going to help us very much. But if we hit one of these two, since every single rule upstairs for S has exactly one character on either side, therefore, if we hit one of these two rules, which we must do to make a string, that means that we have, in the same position on either end, we have differing characters. And so therefore, the string is not a palindrome. But it's not important that this grammar has that particular language. I wanted something that is somewhat non-trivial. Okay, so let's do the context-free grammar to PDA conversion. Obviously, there are many different PDAs that you can make, but it's important when we talk about a conversion like this to be able to apply it to any context-free grammar, not just this one. We could specially make a PDA for this grammar, but I'm going to do a general conversion that works for any grammar, so you don't have to work with this specific one. Okay, so what do we need to do? Well, if we think about what a general context-free grammar does, what we do is we start with the start variable, and then we apply a rule. So this double arrow means apply a rule. So that means we're going to get something on the right-hand side from applying that rule. Then maybe there's an S in here, although it doesn't have to be. We could immediately jump to the P variable here, but let's just say there's an S. Then that means we're going to apply some rule to this S, and then we're going to have something over here. Then we may have another variable, maybe there's a P here, and then we just keep going until we arrive at some string which has no variables whatsoever in it. And that's important because the language of the grammar is the set of strings that you get that happen to have no variables in them. Well, if we think about what a context-free grammar does, let's just imagine some particular derivation that we make, so this is obviously called a derivation. If we have a derivation, and let's say that we have an S variable right here, that's the thing that we're going to replace. Well, if we have a context-free grammar, we're always replacing one variable with stuff. And so therefore, we're going to replace that with stuff. But all the other things on either side are not going to be replaced. And so therefore, the stuff over here could be in principle anything. It doesn't depend on where this particular S is in this right-hand side so far. So what we can do to make this even simpler is to focus on when this variable S right here, although it doesn't have to be S, is the first variable. So over here, there are no variables whatsoever. And over here, there could be in principle anything. But if we have the leftmost variable, therefore we can always work with that without loss of generality because we have a context-free grammar. Okay, so then if we focus on this, well, how do we get this to a PDA, which involves states and a stack and all of this kind of stuff? The idea is actually really, really simple. So all you have to do is to take this right-hand side and then just do a 90-degree change to it. And by 90 degree, I mean literally 90 degrees. And what I'm going to do is this right-hand side, well, this is all the right-hand side, but the right end of this is going to be coming down to the bottom here. So notice I do this 90-degree transformation. So let's say that this right-hand side was W1, W2, W3, up to Wn, where these could be variables or terminals, it doesn't really matter. Then what we're going to do is, the goal being to have a stack, because that's what the PDA needs, with this particular configuration. So take this right-hand side right here, and I'm going to move my right finger down 90 degrees, so now it's at the bottom. So the Wn is going to be at the bottom, then n minus 1 above that, and then etc. up to W3, W2, W1. So W1's up top here. And why is this important? Because the PDA is going to be reading characters left to right. So if this is the string we eventually make, so this is not just one rule application but many, if this is the eventual string that we make, then that means that this thing is the first character that's going to be read in the PDA. Which means that if we're going to be storing this on the stack and then working with the stack as we go, then this thing must be at the top of the stack because that's how stacks work. You can only pop off the very top of it. So that's how the general procedure is going to go. Well, the problem is, well, what if this very first thing is a variable, like s or something? Well, then obviously up here, this is going to be an s. Well, then what are we going to do? Well, we can't just read off of the input because the input string has, in this particular case, A's and B's, but in general, terminals. Whereas here we have a variable. So if we have a variable, whenever we have a variable in the derivation, if it's up at the top in the stack, and that's coinciding with this, that means that there's nothing to the left of this s right here. Which means that it's the leftmost variable, and therefore we can apply some rule to it. So the goal being, in the PDA part, if we see a variable upstairs, let's apply a rule to it. And so this is how it's going to work. So how are we going to make a PDA for this? Well, every single derivation in any context-free grammar whatsoever always starts with the start variable, obviously. So, but the PDA stack doesn't have anything on it whatsoever to start with. There are some textbooks that have some kind of preliminary character at the top of the stack, but let's assume that there are no characters at the top of the stack. But then we need to put something on. So what I'm going to do is I'm going to have a state Q0 right here. And what I'm going to do is I'm going to read nothing. So I'm actually going to use... So on this first transition, what I'm going to do is I'm going to read nothing. So this is the read position. So the way I'm going to format my transitions is read first, then pop, and then write. So I'm going to read nothing here. Well, I can't pop anything here because the stack's empty, and then that would be kind of pointless. So I'm going to pop nothing. So this is the pop one. So pops here, reads here. Make that arrow a little better. And then what I'm going to push, so this arrow means after the read and pop happen, which happen to be doing nothing here, then I'm going to be pushing something. So I'm going to be pulling something out of a little hat right here, and I'm going to be pushing on a $, because I want to get rich, obviously. But the real reason is that this is going to come in handy later. So I'm going to go to a state right here, Q1. So at this point right here, the only thing on the stack is the $, obviously. But then now let's get into the meat of the business. And here we're going to start the derivation, and every derivation starts with the start variable, obviously. So I'm going to do exactly the same thing. So I forgot to say this is push. I'm going to do exactly the same thing, except I'm going to push the start variable of the grammar, which happens to be s in this case. But whatever the start variable's name is, that's what's going to be coming here. So I'm going to be reading nothing, I'm going to be popping nothing, and I'm going to push on the start variable, which happens to be s here. If it was called x in your grammar, it would be x here. And then now I'm going to go to a state I'm going to call Q loop. So at this point right here, at this particular moment, we have this $sign at the bottom and S at the top. And that's all that's in the stack so far. Well, what are we going to do here? We're going to have this state be representing, look at the top of the stack, and then do something. So the top of the stack can be one of three things. So the top of the stack can be one of three things. I'm going to write some notes right here. So it can be either a terminal, obviously, because we're going to be simulating a derivation, and derivations involve terminals and variables. So there can be a variable at the top of the stack, in which case there is right here. Or three, we can have the $sign at the top of the stack. Okay, well, if the $sign's at the top of the stack, we're never going to be putting on another $sign. This is the only one. Apparently I don't want to get that rich. But if the $sign's at the top, that means that there's nothing above the $sign right now, which means that there's nothing left to look at anymore. And so therefore, we're effectively done with the computation. And so therefore, I'm going to do a similar type thing, but I'm going to pop off the $sign, which means that I'm observing that there's a $sign. I need to do this transition only when there's a $sign on top. And I could push something, but there's no point here. And I'm going to go to a final state right here. So the final state is saying, we're done at this particular moment, and this will be the only final state of this machine. Okay, we need to actually verify that this actually does the right thing, but that involves, well, fixing the rest of the machine. So what do we do in the other cases? Well, if there's a variable at the top of the stack, that's because we're trying to simulate a derivation, and then therefore, if we have a variable at the very beginning, that means that we need to apply a rule to it. But I'm going to skip that for now. I'm going to talk about the terminals first. So if there's a terminal at the top of the stack, let's try to just see what that would look like. So let's say that there's S here, and then maybe some other stuff, and then let's say that there's an A up top. Well, since it's a context-free grammar, I can't actually apply a rule to a terminal because I can only apply rules to variables. And so therefore, this A is going to be permanently fixed in the grammar's derivation because it can never be replaced. In other types of grammars it could be, but in a context-free grammar it can't. So then what can we do here? Well, since we're reading off of the input in the PDA, we can just say, well, if there's an A at the top of the stack, and we are reading an A off of the input, or we desire to read an A off the input, let's do both of them at the same time. Because we want the PDA's language to be identical to the context-free grammar's language. And so what we're going to do is a bunch of self-loops right here, although they don't have to be self-loops, but it's a lot easier. What I'm going to do is I'm going to do a read and a pop of each of the terminals at exactly the same time and no pushes at all. So here I'm going to be reading an A because A is a terminal in the grammar. I'm going to be popping an A and then pushing nothing. And similarly with the B, because it's also a terminal. And if there were other terminals, we would be stacking them up on this self-loop, set of self-loops right here. And why is this a good idea? Well, think about what's going to happen. So we're going to have the input, let's say, is A, B, A, B, just as an example. So if we're in Q loop right now, and we're in this situation where we have an A to pop off the stack, or as at the top of the stack, I should say, and an A to read, well, here I can't apply a rule, and this is going to be the only transitions that read or pop these particular terminals right here. And so therefore, this is going to be, since that's the only transition, this is going to be popped off, and I'm going to be reading this A off of the input. And we're trying to non-deterministically generate this string because context-free grammars are non-deterministic, and so PDAs are also non-deterministic. And so therefore, we're going to be reading a character here, and since the A in the derivation is never going to change, we're quote-unquote reading it, even though we're not actually reading it because we're popping it off a stack. But they're being dealt with at exactly the same time. Okay, so we got the terminal working, and we have the $sign working. How do we do the variable? Well, that's where all of these rules are going to come into play. So I'm going to try to do all of these. It's going to be a huge mess, and I'm going to probably use a different I'm going to try to use a different marker here to try to differentiate it. So let's deal with this rule first. So that's saying if we have an S at the top of the stack, I want ASA to be replaced. So let's say that we have some derivation right here, and we got some stuff, and we have an S right here, along with some other stuff, and then we decide, oh yeah, I want to apply this rule. So then I'm going to have some stuff, the same stuff, and then ASA along with some other stuff, because I'm replacing this S with ASA. I'm replacing it. So that means that in the grammar, in the derivation, we're replacing only this little bit right here. But if we do our little finger trick, this thing on the right-hand side needs to come down. So if we think about it this way, this A right here on the right is going to be on the bottom. So the left A is going to be on the top, and the right A is going to be up at the very top. The left A is going to be at the very top, and the right A is going to be at the very bottom. So that means that the rule of so how you actually put this particular right-hand side onto the stack is somewhat unintuitive, but the idea is to take this rule, the idea is to take this right-hand side and push it onto the stack in reverse order. Because how stacks work, the last thing that you put on is the thing at the top. So that means that this A on the left must be the last thing that we put on, not the first thing. Even though the rule is completely symmetric in this case, so it doesn't really matter in this case. But again, we want this to be algorithmic. So what I'm going to do is I'm going to have a transition, or a set of transitions, which are not going to read anything. No other transition is going to read, by the way. But we got to take this S off because we're replacing that S with other stuff. So I'm going to do it this way. There are many ways you could do this, by the way. So I'm going to pop this S off. That's saying we're replacing this S with something. And then here, I'm not going to name the states because there's just going to be so many. And then after that, I'm going to push this rule in reverse order. So this A is going to be put on first. So that means I'm going to not pop anything, push an A, and then push an S, and then come back with pushing the last A. So that means that I've taken this S off and I've replaced it with the whole of the right-hand side of that particular rule. And then now we got to deal with all of the other rules, obviously. So there's going to be a lot of things that we're going to do, so I'm going to try to make this as non of a pain as possible. So now we got to deal with this one. So S goes to BSB. So I'm going to, so the technically correct thing to do is to make a separate set of loops for each one of these particular rules. But since it's going to be popping S off every single time, it doesn't actually matter if we just chain on this one. I can't actually deal with this for reasons that you should think about. So what I need to do is to make a different set of two states right here. So I'm going to deal the BSB rule right here. So this is going to do this. And then I'm going to push on B. So this rule is done. So I don't need to focus on it anymore. And then now we have the P rules. And so I'm going to make some more room. And I'm going to do a set of two more sets of transitions here. So we need to pop off S here. So that's I could piggyback off here. In fact, I'm going to do that. So I'm going to piggyback off of it, where I'm going to be now pushing on this one. So this is the rule I'm dealing with right now. So B goes on first. So in fact, I could even piggyback off that one too, but I'm not going to. So I'm going to push on the B here. And then since we're going in backwards order, the next thing is the variable P. So P goes on. So this is going to be push on P. And then come all the way back on pushing A. So epsilon, epsilon, A. Okay, so that's dealing with S goes away, B goes on, P goes on, A goes on. In fact, since these two rules are completely symmetric with each other, it doesn't matter which one you do first. In fact, it doesn't matter if you happen to do them in opposite order because they're both opposites of each other. But again, we want this to be general and algorithmic. So I'm going to try to piggyback off of this one more time. So here I'm going to do, so that rule's done. I'm going to try to do this one. So I'm going to do epsilon, epsilon goes to A. And then I'm going to push on P, epsilon, epsilon, P. And then go all the way back to on pushing B. So this is getting really tight. So one of the things that you should notice is that all of the things that we're doing here are completely algorithmic. I don't have to rely on special properties of this grammar other than what are the variables, what is the set of terminals, what is the set of rules, and what's the start variable. I don't care what language it is at all. That's all the information that I need. I don't need to know the structure otherwise. So then now we deal with all of these. So now let's deal with the P ones. So now we have a different variable to pop off, so we can't piggyback, obviously. So that's why we made more room. So I'm going to pop off P. So pop P off. And you could try to squeeze this a little bit by pushing on something right here, but I'm not going to because I want to chain multiple rules together. But I'm not going to, but you can absolutely put something on right here. So I'm going to do this one first. So here I'm going to be pushing P back on, which is kind of weird, but I might as well do it. So I'm going to push P on, so epsilon, epsilon, P, and then go all the way back on pushing A. And then, so this one's done. So take P off, put it back on, and then push A. So I'm doing this rule in reverse order. And then now let's deal with this one. So I'm going to again piggyback off of this. In fact, I can piggyback off of it completely almost. So here it's again here again it's going to be popping P off, pushing it back on, and then pushing now something different. So I can just add another transition right here. Goes to P, goes to B in this case. So this one's done. And then now all we need to do is to add a rule for this one, which is popping P off and then pushing nothing back on. So obviously there's nothing here. And we can actually piggyback off of this. Another thing we can do is to do another self loop here, which is essentially this transition, but a self loop, which is effectively what that rule is doing. But here I'm going to do a transition from here. So here it's going to be literally doing nothing to the stack, not popping, not pushing, not reading, nothing. So epsilon, epsilon goes to epsilon. And laboriously, we are finally done. So we've converted this context-free grammar into this particular PDA. Obviously, there are many other PDAs you can make. You can make a lot smaller PDAs, but again, for the 5,000th time, this is a particular algorithmic choice that I'm making here. I'm not relying on any specific properties of this particular context-free grammar. I want this to work for any context-free grammar. You're unlikely to have exactly this context-free grammar, so I want you to get the process, not the I want you to get the process, not the exact answer that you get here. That's not the point. The process is the important point. So let's actually verify correctness. So if we have a derivation up here, that means we have a certain set of, so let's verify correctness. So if we have a derivation in the now partly erased grammar, well, that means we started with S and then eventually made our way down to here via some set of rules. Well, does that translate to a set of transitions and accepting in the PDA? Well, let's see. Well, we start here. We can always execute that transition. Always we can execute because we're only just pushing stuff off. Well, so all we need to do is to look at what rules did we apply. Well, if we applied, let's say that one, that means that in this case, we had the choice in the PDA of applying the associated transitions for that particular rule. And if we applied this one, we had a choice of applying this one. And so there are many different choices that are made, but the key here is that these transitions are going to cause us to read. So these transitions are going to cause the PDA to non-deterministically choose the exact set of rules that were made in the context-free grammar, and not just any set, because the PDA could apply any of these loops any way that they want to. These set of transitions are going to stop it from just doing whatever it wants. So if we eliminated these, this PDA could do whatever it wants. And, well, in fact, it can't read anything, but it could do anything it wants with the stack, essentially. So that would imply that we got all the way through the characters, because in the CFG, if we had a derivation, we got all the way to a string of just terminals, which means we got to here, which means the stack had all of its terminals, which means that we read through all of them, which means that we got to the bottom of the stack, which is where this thing comes into play. Because there's no way in a PDA, at least in most models, to detect whether the stack is actually empty. So therefore we have this bottom of stack marker to detect that for us. And so now we can actually accept. Well, if we had a different string, if we had a longer string than what the CFG had before, well then that means that we get to here and we don't accept, because the PDA's behavior is, if you get to a final state and you haven't read the whole thing, meaning the whole string, then you don't accept, which is exactly what we want. Well, if we had so let's do the converse direction. If we had an accepting computation in the PDA, does that translate to a derivation in the grammar? Well, the computation path must start here because it's the start state. Then it must push on the $sign, must push on the S here, and eventually must make it here because we assumed we had an accepting computation, which means we must have popped off the $sign right here. Well, how is that going to happen? Well, that means that everything above it on the stack must have gone away, including this S. So this S must have gone away, including anything that could have happened before that. Well, then that means that no matter what we had, the entire string was read because we got to here and we accept it. So if we read the entire string, these are the only transitions that read. And so therefore, we must have had all of the corresponding terminals on the stack at some point, which means that we had a derivation up here. And if you look at what the paths were in the PDA, that corresponds one-to-one with each of the rules in the context-free grammar. And so therefore, if there's a derivation up here, there's an accepting computation here, and vice versa. So hopefully that was interesting. Leave thoughts about the CFG to PDA conversion into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.